Here in this problem, we actually are going to build a quadratic equation. So the goal is basically to create an equation that predicts the outputs based on the number of plants that can possibly be useful later on. Okay, well, assuming this is perfectly quadratic, which I believe it will be in this case, we should be able to determine a few things. Well, first of all, c is the initial value. So when the input is 0, the output is 7. So that is, when the number of plants is 0, we should have 7 bees present. So that means that the number of bees present is equal to A times the number of plants squared plus B times the number of plants plus C. Well, right now we know that this guy is 7. Okay, approximate B from the data. So that's the initial rate of change. Well, the initial rate of change, the best we can really do is say, well, from the 0 number of plants to 1 plant, the change in the number of bees is actually 3. So we would approximate that the initial rate of change is about 3. Now in a second we'll show how we can get this more precisely. Now this is kind of an estimate. So this is an estimated value. We're kind of using the best of our knowledge with respect to the data to find this. Now A is related to the change in the rate of change. So we'll actually calculate some of these. So at first the number of bees increased by 3, 5, then 7, then 9, then 11 as the number of plants increases by 1. Well, we see a trend. We see that the change in the rate of change is 2. That the number of additional bees that you get by adding plants, for each additional plant you add, you not only increase the number of bees that are present, but you also are doing it at a faster and faster rate. So the number of bees, well, initially it starts at 7, goes up by 3, then goes up by 5, then goes up by 7 as the inputs increase. So we actually have a growing rate of change. Okay, well, so that means A, we've noticed the pattern that the change in the change is equal to twice the value of A. The change in the change in this case is 2, so 2 equals twice A. That means that A is equal to 1. So we know that our equation should be B equals 1p squared plus 3p plus 7. So let's check it. Let's see how we do. If I put in 0 for p, I get 0 plus 0 plus 7 is 7. Perfect. So I predicted this output exactly. If I put in 1, I get 1 plus 3 is 4 plus 7 is 11. Not quite 10. Why is that? Why am I not getting exactly 10? I'm actually getting 11. Well, because we had an estimate here. This is not exact. If I were to even go to 3, then I would get 3 squared. 3 times 3 is 9. 1 times 9 is 9. Plus 3 times 3, that's 9. So 9 plus 9 is 18. Plus 7 is 25. So I'm even more off right here. So just to show you, so we have our equation. We've sketched the graph. Just to show you off to the side now, well, how would we get, oh, maybe I'm going to use n for the number of bees so I don't confuse, because it looks like I have 2 bees in this equation. So I'll say n equals the number of bees. Okay, well, let's just say I decided, you know what, I'm not comfortable with an approximate form. I want to know B exactly. Well, what I could do is I could use an ordered pair and plug in a pair of those values. So I know that 10 bees will be present when I have 1 plant. So I'm going to replace all the values that I know in this equation with ordered pairs. Okay, so my only unknown value is B. That means that I can actually simplify here a little bit. 1 squared is 1. B times 1 is B plus 7. So I know that 10 equals B plus 8. Now, so this is a basic linear equation to solve. We've kind of combined similar things here, and if I subtract 8, I get that B is equal to 2. So as a matter of fact, our estimate was close, but no cigar. We weren't exactly there. If we used B equals 2, we should be able to predict these outputs exactly. So the exact equation would be p squared plus 2p plus 7.